Okay, so here we have a first derivative of xy cubed. We have a second derivative of this, and we're trying to find the equation of the tangent line to the graph of y equals f of x at x equals 1. So telling us this information here, f of 1 is equal to 2. So I know from f of 1 is equal to 2, I know that that is the point 1, 2. So if I'm trying to find the equation of the tangent line, the first thing I need is the slope. So if I try to find f prime at 1, that means that I have to plug in 1 and 2 respectively, and for the x and the y in my first derivative. So I'm going to plug in x was 1, y is 2, so 2 cubed. That's supposed to be a 3 up here. So if we do this, we end up with 8, and 8 is equal to our slope. So once we have our slope, and then again we know this point of 1, 2, we can use point slope form. So we're going to do y minus the y value. So our y value here is 2 equals the slope, so 8, x minus the x value, so x minus 1. Okay, so you can leave this as your answer. If you want to solve for y, you can get y equals 8x minus 6. Okay. So for part B, use the tangent line equation from part A to approximate f of 1.1. So 1.1 is the x, and we're trying to find y. So that's why solving for y is actually easier in this case, getting it into y equals mx plus b form. That way we can plug in our x value. So for our approximation, we're going to do f of 1.1. So that's going to be equal to 8 times 1.1 minus 6. So then we actually do that. So that's going to give us 8.8 minus 6, which is going to give us 2.8. So 2.8 is our approximation. And then it wants us to know that if x is between 1 and 1.1, is the approximation for f of 1.1 greater than or less than the actual value of f of 1.1? And explain. So for that, we have to kind of think about what this graph is going to look like. So they're telling us f of x is greater than 1. So what that means is that if I had, some graph, if the function is greater than 1, it's got to be somewhere up here. Okay, it doesn't look like that squiggle, but it's somewhere above the x-axis since it's greater than 1. Then they're telling us up here about the second derivative. So if we know the equation for the second derivative, what we can do is we can plug in the point 1, 2. So at 1, 2 in the second derivative, so f double prime, I'm going to say at 1. I'm going to plug in 1 and 2 into here. So when I plug in 2 for y, so 2 cubed, and then 1 plus, this would be 3 times 1 times, it's supposed to be parentheses, 2 squared, so that would be 4. Okay, so if I figure out what this is equal to, this is going to give us 8 times 13, right, which is greater than 0. So since that value is greater than 0, and it's the second derivative, if it's greater than 0, we know that it's concave up. So if I think about this, if it's concave up, then the tangent lines that I draw have to be below the graph. So when I have concave up, all my tangent lines are going to be below the line, or below the function. So our approximation of 2.8 is going to be less than what it actually is, since the tangent lines are below the curve, meaning that they are less than the actual values. So I can't rate so good, so I'm just going to say what it should be. But you want to state for your answer that since f of x is greater than 0 on the interval and the second derivative is greater than 0, then the interval from 1 to 1.1, the line tangent to the graph of y equals f of x at x equals 1 lies below the curve, and the approximation to 0.8 is less than f of 1.1. Okay, so continuing with that same problem, now we have to find the particular solution, y equals f of x, with initial condition f of 1 equals 2. So whenever you see that word particular solution, what this really means is that you are going to have to do the separation of variables, and you need to get the y's on one side, the x's on another, and take the antiderivative, and then since you have an initial condition, you have to plug it in and solve for c. So first thing we're going to do is write down our first derivative, because when we do separation of variables, we're only dealing with the first derivative. So dy over dx is equal to xy cubed. So if I want to separate the variables, I need to move the y cubed to the other side. So I'm going to say that this is 1 over y cubed dy, and that's equal to x dx. So I'm separating those variables by moving the y's and the x's accordingly to the same side. So I'm going to rewrite 1 over y cubed as y to the negative 3 dy, and keep this as x dx. So what we can do now is take the antiderivative of each side. So when I take the antiderivative of y to the negative third, we're doing the reverse power rule. So we're going to add 1 to the exponent, so it becomes negative 2, and then we divide by negative 2. So what we really have is negative 1/2 y to the negative 2. And then on the other side, we have x, so that's going to become 1/2 x squared plus c. So from here, our goal is to get y by itself. So first thing that I can do is I can, I'm going to rewrite this actually as negative 1 over 2y squared equals 1/2 x squared plus c. Okay, so what I'm going to do from here is I'm going to multiply both sides by 2 to get rid of this 2 in the bottom. So multiply by 2, multiply by 2. So I'm going to get negative 1 over y squared is equal to x squared plus c. So even though I'm multiplying c times 2, it's still a constant, so c. So I'm going to put this over 1. So we see that there's a fraction equal to a fraction. I need y squared to be on the top, so I'm going to flip both of these fractions. So this is going to become y squared over negative 1 equals 1 over x squared plus c. Okay, so then from here, I'm just going to get rid of the negative with the y squared and move it over here. So I have y squared equals negative 1 over x squared plus c. And then I need to get y by itself, so I have to take the square root. So I'm going to get y is equal to, when I take the square root, I'm going to make the negative go in the bottom, so I can make this like the square root of 1, which is just 1. And then on the bottom, I have the square root of negative x squared plus c. Okay, so when we do negative, remember negative can be either on the top or the bottom. It's technically like outside. It doesn't go to both. So because I can't take the square root of a negative 1, I moved it down here. Because the x squared is attached to the c, it's okay to take a square root, because if this is a negative here, right, this could be positive enough to make it not an unreal answer. So we are just going to keep it like that. So this is where we're at currently. So what we need to do is now use our initial condition and try to solve for c. So our initial condition is that y is equal to 2, and x is equal to 1. So we're going to do 2 is equal to 1 over the square root of negative 1 squared. So 1 squared is just 1, so we're going to keep that as just negative 1 plus c. Okay, so then what I'm going to do is I'm going to put this 2 over 1, and I'm going to flip it again, like change the top and the bottoms, because I want to get this c by itself. So I could cross multiply, I could flip it, kind of do what makes sense for you to do. So if I flip it, I'm going to get 1/2 is equal to the square root of negative 1 plus c. Okay, so now I have to square both sides to get rid of the square root. So square both sides. So I get 1/4 is equal to negative 1 plus c. So then I get that c is equal to, so I'm going to add 1 to the other side. So c is equal to 5/4. Since I know what c is equal to now, I can plug it back into my equation to get y. So y is equal to, I'm going to go back to this equation, and I'm going to plug in 5/4 for c. So I have 1 over the square root of negative x squared plus 5/4. And then that would be our answer. Oops.